Now I share my screen. I hope you can see my screen. Can one of you confirm that you can see my screen? A thumbs up sign. Yeah, thank you.
Yes.
That's what I'm looking for. So, okay, so where were we last time? Right, and we were in session one. Right. So we looked at data distributions, right? And so basically there are three types of distributions broadly. Okay, those with a positive skew, those with that are symmetrical, and those that are negative, right? And in general, what that means is that if you have a negatively skewed distribution, it means you have a long left tail, like on the right hand side here. So what that means is that the mean of the distribution is decided by all the values in the distribution, right? So because you have a long left tail, the mean is dragged back. Okay, and when that happens, you have the mean being less than the median, which is less than the mode. Okay, the mode is the most frequent element, right, in the probability distribution or in a table of numbers. I think one of you has to go off onto mute mode, okay, because otherwise there'll be a problem. And then you have the median, which is between the mean and the mode. That's negative skew. Now, if you look at the other side, where it's effectively a mirror image, you have now a long right tail, then what that will do is that it will drag the mean to the right-hand side. So the mean will be the largest thing there, okay, because you'll have a lot of highly positive points that are dragging the mean to the right-hand side. But then the median will be between the mode and the mean, right? So so it's either mode is less than median is less than mean. That's for positive skew, or mean is less than median is less than mode, which is the negative skew, right? Now, if the distribution is symmetric, then all these three things will coincide: mean, median, and mode. So you see this for a Gaussian distribution, that the mean, median, and the mode are all the same thing. So you have 50% of the curve is less than this point, okay, and 50% is more than this point. The highest, the most frequent value in the distribution is also the midpoint, right? That's the median. And the mean, because it's symmetric, will also be the midpoint. So a symmetric distribution has all these three things essentially coinciding. Okay, so that's basically the idea. Okay, so that's so the mean, which is a measure of central tendency, median, mode, and so on, is just a single number, right? Now you have a bunch of numbers which are in the distribution or a table of numbers, and then you can ask legitimately that if we were to summarize that table by a single number, aren't we losing something? Okay. Now, from an information point of view, it seems that something has to go, right? Because you can't uh, take a large number of numbers and somehow hope to summarize that set of numbers by just a single number. You just don't have enough information there, right? Because so now the thing is that insight is correct. Okay, but how do we actually show that that insight is actually correct? So what we'll do here, we have a bunch of numbers. Okay, now it will turn out that the mean, median, and mode are the same for all the distributions of numbers that we are going to talk about here. So for example, you have about 9 numbers here. So you see that the mean is 2 plus 8 plus 5 plus 3 plus 7 plus 8 plus 5 plus 2 plus 5 divided by 9 turns out to be 5. Okay, 45 divided by 9. Now the median is also 5, as you can actually list the numbers out in ascending order and pick the middle number. That's the median. Now the mode is also the most frequent number, which happens to also be 5. 1, 2, 3. 5 occurs 3 times. And then you see that none of the other numbers occur the same number of times. Okay. So for this set of numbers, mean, median, and mode are all the same thing. Okay. Now, if I were to change the numbers, right? Now look at this now, this table again, it's quite different from the previous one, right? So you have a different distribution of numbers. If you look at the statistical measures on the right-hand side, right, you have again mean, median, and mode, which are all 5, just as before. Now, if I'll compare these two tables, you can't say these two tables are the same, right? So second table has a different feel to it. It has an outlier like 15, right? But that number 15 isn't entering these calculations, right? So now the thing is, you can have a distribution or a set of numbers that are very different, but which can end up having the same measures of central tendency, whether it is mean, median, or mode. It's all the same, 5, right? So you can actually do the calculation for yourself and see that the sum of these numbers is 45. So the average, which is the mean, is just 5. The median is again 5, because if I were to reorder these numbers, the ranking of 5 will not change. It's still the middle number. What's happened is that we have moved one number on the right hand side further to the right. Okay, that's not captured in the median, because the central number, the middle ranking number, is still 5. Okay, now you say, okay, I have moved 15 to the right, right? I had some number to the right, I made it 15, so I have moved it to the right. So the mean should change. But what I did there was to readjust the other numbers so that the mean would stay the same. So somehow I have a different distribution of numbers, right? But the same statistics. So the thing is, it's no longer informative, right? So this is not informative. Let me just second. Should be able to write on this. This was a problem last time also. I'm not sure how to actually get the pen to write here. Okay, anyway, let's go over here. So the mean, median, mode. Not informative. Not informative enough, I would say. They give you some information, but not informative enough. Okay, so same mean, median, mode, very different distributions. Okay, so that's the problem. Okay, so this here the third example. You have yet another table, and so this has the same mean, median, and mode, but then again it looks different from the previous one. Okay, so now the thing is, uh, if you look at the issue, right? The issue is that a measure of central tendency simply captures where one number is, which is where the center of the distribution is, so to speak. But it doesn't tell you anything about the spread, right? So what are the real problem that we just encountered? If I imagine that this is your distribution, so let's assume we don't even know about probability and so on. So I'm just giving you some kind of an intuitive feel for what a distribution is. Okay, so don't worry about the uh, the actual mathematically rigorous definition of it. We don't need it. Okay, just assume that you have a distribution of numbers and say some numbers are here, slightly more numbers are here, and then more numbers are here in this bracket, and so on and so forth. Okay. Now the thing is that if I take the mean, yeah. So if I take the mean, what will I do? I'll count the number of numbers here. Say this is n1. I'll count the number of numbers here. This is n2. I'll count the number of numbers here. Let's say this is n3, right? Then I say that these n1 numbers are located at this position. These n2 numbers are located at this position. N3 numbers are located at this position. So what I'll do is the mean will be n1 numbers located at position x1 plus n2 numbers located at position x2 plus n3 numbers located at position x3 plus say nk numbers located at position xk. That's on the right hand side. Okay, so this is xk and this number of numbers is nk. And then I'll say that somehow I have to add up all of this stuff and divide by the total number of numbers, which is nk. Right? And then what will happen is the mean will end up pointing somewhere here. Okay, this will be the mean. Now, the problem is that I can make this distribution be something like this, right? So the next page, I can take the same distribution. Let me overlay the two distributions on each other. The first guy was this, right? And this was the mean. Now the second guy will be something like this, right? This is the first distribution, and this is the second distribution, right? Now, if you notice, both of them have the same mean. So all that I've just done is that I've spread the mass out. Okay, so whereas here you had n1, say this was x1, now you have the same n1 prime at x1 prime. Okay, so what I've done is that I have taken the n1 numbers that were in the first bin of the previous distribution and spread them out to further to the left, right? I've done this, I've done some kind of rebalancing. So rebalancing of data has essentially spread the data out. Okay, we can spread the data out. Okay, okay, we can spread the data out, right? And still have the same mean. That was the phenomenon. So the thing is, we need at least one more number to characterize a distribution. Something about spread, right, should be there as part of the description that we are using to describe this bunch of numbers. Otherwise, it's an incomplete picture. If I don't have spread, then I really don't know what goes into how the distribution is composed. I just have the single number, it tells you what the middle number is. Whether the middle number is mean, median, or mode, okay, it's very limited. I mean, okay, that's the middle, but what about the flanks? The flanks are not being described, right, by that single number. So one more number I can think of is somehow to capture the spread, right? So how do we capture the spread? So do we need any other measure? The answer is yes. And we
Sir,
want go ahead.
sir, sorry to interrupt you.
Yeah,
Sir,
sure, sure. Go ahead.
like, was there any basis of sort of spreading it out, or you just give an example, or I
It's an
could not get
example.
that.
Yeah, yeah.
Okay,
See, the
okay.
thing is
It's
that
just a
this
random
data
example.
comes from the field, right? So let's assume that you're a salesman, right? And you've gone around looking at the income profiles of all your prospective customers. Okay. Now you have 1,000 customers, and what you did was you went around these 1,000 people, collected their income data and so on. Then you came back to your office and you plotted a histogram, right? Now you do this for one locality, you get one type of spread. You do it for another type of locality, you get another type of spread, right? Now
So
let's
your
assume
whiteboard
that,
is not visible. Your whiteboard is not visible. You have
yeah,
overlaid
I'm
it
just
with the.
explaining to you
Okay.
verbally.
Okay.
So,
Sure,
okay,
sure.
I'm explaining it to you verbally, all right? So I'm saying that, look, there are two localities, right? In locality one, you collected income data from different people. If you want a whiteboard type of example, let me go back to that and show it to you. Look at, let's say this is first distribution. Let me put this as income data. Okay. And this is the second distribution. It's also income data from locality one. And this is from locality two. Right. Now, in the first distribution, I found that there were a bunch of people who are earning a fairly large amount of money. Okay. So the first locality had a bunch of people who were earning a large amount of money, and then the spread wasn't that much. Okay, so if you turn out, suppose this was 100,000, say let's give it in Indian rupees, right? Let's say this is 10 lakh rupees. Then we found that around 15 lakh rupees, there's pretty much nobody earning anything there. Okay, nobody falls in the 15 lakh bracket. And then if you take the 5 lakh bracket over here, then again you see very few people falling into it. Okay, that's the data that you got from the first locality. But you look at the data from the second locality, it's a different picture. There you don't see quite so many people earning 10 lakhs. Okay, whereas if you say maybe 10% of the population was earning 10 lakhs in the first locality, that number is now something like 7% in the second locality. So that 3% is the shortfall, right? So that 3% got distributed into other bins. And then what happened was you could have more people earning more than 15 lakhs now. Whereas in the first case, you had only, say, 1% of the people earning 15 lakhs. Now you have, say, around 3-4% of people earning 15 lakhs, and there are also people earning more than 15 lakhs. There's also people earning less than 5 lakhs. So the variability is more. How do you capture that? Right? So basically, I could have different types of curves, and they're capturing different nuances of the data I have collected. See, when you collect data, it's just a bunch of numbers, right? Now, like I said in the beginning, if you collect a bunch of numbers and then say, give me a single number to describe that bunch of numbers, then I'll pick the mean or the median or the mode, right? But then that number is going to be incomplete. It won't describe the entire data that you have. So the mean doesn't tell you just how many people there are on the flanks. You get the picture now from this example?
Yes, sir. Thank you. Thanks a lot. Makes sense.
Okay, thank you. So let us move on. So over here,
To
right?
sorry to interrupt, sir. One question here.
Yeah, go ahead, go ahead.
Sir, in this case, what should be
Hmm.
the input criteria? So what I understand is like when the mean are for the different data set, if the
Huh,
means are same, then
huh.
only we should go to this approach, right? When the mean is not sufficient and when we have a
Yeah, yeah,
dispersion of the
yeah,
data.
yeah, yeah, yeah,
Okay.
yeah, yeah. So
Okay,
no,
sir.
so the thing is that, see, the mean is called the first moment. Okay.
Okay.
See, it's something like this. Now, a distribution, like since we don't have a formal definition of a distribution yet, I can't get too mathematical. Okay, but I'll give you some sort of an idea. So a distribution has a bunch of numbers, right? Now I showed you a continuous distribution. You could also talk over discrete distribution, where instead of having the numbers spread all along the real x-axis, you have numbers concentrated at distinct discrete points. Okay, that's a small nuance, but the issue is something like this. If you give me a bunch of numbers, whether they are from a continuous distribution or a discrete distribution, the first question I can ask is, okay, so what is the average? That's the first question. And the average will be something, right? Then people say, okay, this is the average, looks pretty high. But then thing is, I'm not totally convinced that, let's take the performance of students in an exam, right? So you're running a school, there's a bunch of students in the school, they scored some marks in an exam, right? Now the school inspector comes in and he wants to assess the quality of the school, right? So he says, okay, uh, let's take the average of the performances of all of the students in the school, and this average turns out to be pretty high, right? So the principal of the school is very happy because average is high, right? Then this guy says, okay, that's not terribly satisfying because the average could have been pulled to the right by one person's exceptional performance, right? So you have your, so if I were to further animate this example, let's say you have a poor school in the suburbs. Okay, it's a small school that's there in the suburb. Generally, it has poor performance, but in 1 year, one person did exceptionally well, right? So that pushes the average to the right. And then if I just looked at the average, right, then you get a false picture of the school's performance. What's important for you is not just the average, but also the spread. Okay, so that spread, you have to capture that spread. Maybe the average is high because of one guy getting a very high score. So, but how did people in the school in the school generally do? What was the spread? Were there many failures? There could be, right? There could be a large number of
Mm.
failures also. So the average is 50. Okay, so out of say whatever, but many people are at zero, and one guy is at 1,000. Let's say the 1,000 mark exam, right? One guy is at 1,000, many people are at zero, average is still 50. And there may be other schools where the average is around 45, but there's nobody who's failed, right? So now you get a different picture. So if I just look at a single number, it doesn't tell me enough. So I start looking at other numbers. Okay, because at the end of the day, if you just look at a single number to describe a large amount of data, you're in trouble, right? That's the picture I'm trying to convey here. Does that make
Yeah.
sense?
Yeah, sir, absolutely. This is a best example. Thank you.
Okay. So the question is, how do you measure this variability though? Okay. So there are several measures of variability. One is the range. Okay. The range, as might be obvious, is basically the difference between the maximum element and the minimum element. You say, okay, look, the scores of students in the exam were distributed between this and that. Okay. But even that is not terribly convincing, right? See, because the thing is, all these single number things, right? They're prone to being distorted by outliers. The range is so large. Why? Because there's one guy who was a very poor student and one guy who's a very good student, right? But the thing is, I want to have some number that tells me what happened in between, right? I not just don't tell me the leftmost number and the rightmost number and take the difference between the two. Of course, yeah, that contains some information, but the thing is, it's not sufficient for my purposes because I want to get an idea of the quality of the data, right? I want to get an idea of what the student performance actually was. And this is not enough. Taking one the outlier on the right hand side, outstanding student, and one really poor student, that doesn't do justice to the millions of students right in between, right? So that's the range. Now, you could have something called the variance, right? And then you say in the variance, you say uh, we'll come to what this actually means. Then you also have standard deviations and quartile deviation. The outside of the range, right? The other three measures do some justice to the data in between. Okay, whereas the range only does justice to the outliers. Okay, so how can we define variability? It can be defined in several ways. Okay, it's a quantitative distance measure based on the difference between scores, that was the range, or it describes the distance of the spread of scores or the distance of a score from the mean. Okay, so what you can say is, okay, look, you can ask. It's really a pain to not be able to write over here. I'm not sure how to get this to write. Second. Uh,
So you can
no,
click
not
on the
insert.
draw
Where's
option.
draw? Okay. Oh,
Yes,
here's the
and
pen.
then
Okay,
choose
okay.
the
Yeah,
pen.
then so
Yes.
pen. Thanks a lot. Okay. Yeah, this works. Yeah. So now the thing is, you can say, look, here's the mean, right? Here's an arbitrary score, say 74, right? Now you might want to ask what percentage of the students, right, got a score of 74 when the mean is 70. And if you ask what percentage of students, then I have no option but to go back to the distribution, actually look at the histogram, right? Look at the bin that contains that number 74, look at the size of the bin related to the sizes of all of the other bins, etc., etc. I need the whole distribution. Okay. But then what I'm looking for is to say, give me a number that that places this 74 into perspective. Okay. So if I were to take the average of deviations from the mean, right? Then you say, okay, this is the average of deviations from the mean. Score 1 has this deviation from the mean. Score 2 has that deviation from the mean. Score 3 has this deviation from the mean. What is the average deviation from the mean? And where does 74 sit as far as the deviation from the mean is concerned? Okay, relative to that average. So let's do that that calculation and say, okay, look, let me go to the next page. Say x1 is your first score, right? And then you say, let mu be your mean. So x1 minus mu is deviation of score 1 from mean. What about x2? x2 minus mu is deviation of score 2 from mean, right? And then if I do x1 minus mu plus x2 minus mu plus xn minus mu is the sum of all of these deviations. And let's take the average deviation. So because there were n scores, I'm going to divide by n, right? What's this number going to be? So this number is going to be x1 plus x2 plus xn minus n times mu divided by n. But what about this guy? So this guy is going to actually be n mu itself is 0, right? So why did I say x1 plus x2 plus xn is n mu? Because that's the definition of the mean. Right? By definition. So if I were to just take the sum of deviations from the mean, okay, it doesn't work because the mean is a midpoint, right? It balances out data. There's a bunch of data that has positive deviations from the mean, which will exactly cancel out the scores that have a negative deviation from the mean, right? So this approach won't work. But then I come up with another approach which says, okay, look, let me punish deviation in the same way, whether it's positive or negative. Okay, so what happened here was that positive deviations, large positive deviations, were still getting cancelled out by large negative deviations, right? But if I have both large positive deviations and large negative deviations, it just means that I have a lot of spread in the scores. Yeah, if you have a question, go ahead.
Yeah, sir. Just one question here. In this x1 plus x2 till xn, how this
Yeah,
became n mu? So that I got confused here.
because of this, right? By definition, the average is this. x1 plus x2 plus xn divided by n is mu.
Sir, by
Okay,
that
so
definition,
that is
should
mean,
actually,
right?
Yeah, that is the mean. This is the mean.
That is mean. Okay.
So I
by
just
that
want to
But
take,
definition,
this one
sir,
doesn't translate into the above equation. If this is mu,
yeah.
no, like yeah, this the second last equation. If you look at it, you
Huh.
mentioned n
Yeah.
mu minus
No,
n
this
mu
one
by
doesn't.
n.
Yeah. So what I did was I substituted for this guy. So the equation that
Okay,
I'm
okay, yeah,
interested in
sure.
had x1 plus x2 plus xn minus n mu divided by
My
n.
bad.
Now I substituted for x1 plus x2 plus xn from
so
from the third equation.
Yeah, got
So
it.
answer
So
what does
answer should have
zero
been 1
signifies
minus
here?
n mu.
No, the answer will not be
Mm.
1 minus n mu. Where does 1 come into the picture? It doesn't, right? Because this guy, the guy that I've highlighted here, that is n times mu from the third equation. Because if I cross multiply x1 plus x2 plus xn will be equal to n times mu. I'm plugging in n times mu in place of this guy that's here. So n times mu minus n mu divided by n will be 0.
sir, can
the-
from this point, can you repeat remaining part again now because this question is
Okay, look, let me
equation is
let me redo this whole thing. Okay, I think one of you has to let one of you speak at a given time. Okay, and the rest of you please go on to mute. Okay, there's a lot of okay. Let me see this. See, the idea is that we want to capture some notion of deviation. Okay, so I said, okay, let me capture the notion of average deviation. Okay, so what does deviation mean? Deviation means where does your score stand relative to the mean? Okay, so I have score x1, x2, x3, xn, right? All these scores. Where do each of these scores stand relative to the mean? So I say, okay, deviation of score 1 is x1 minus mu. Whatever x1 is, take that minus mu. Go to score 2 is x2 minus mu, and so on and so forth. So if I take the average deviation, it will be the sum of all the deviations of these n scores divided by n, right? That's the first thing, average deviation. So let me call this average deviation. Okay, so this is what I'm trying to calculate. I'm saying, okay, look, I want to capture variability in the scores by taking something called the average deviation. And then I plugged in these values, x1 minus mu plus x2 minus mu plus xn minus mu. And then it turned out the n score. So I separated out this sum as x1 plus x2 plus xn. And then I have minus mu, minus mu, minus mu, minus mu. How many times? N times. So I have x1 plus x2 plus xn minus n mu. Right? The guy in the numerator here is exactly equal to the guy in the numerator over here. It's just that the terms are rearranged. But then you say, okay, here's x1 plus x2 plus xn. What is that? Now, if you look at the definition of the mean, the x1 plus x2 plus xn divided by n is equal to mu. So if I cross multiply, I see that the sum of the numbers is basically n times the mean. So I can put n times mu in place of x1 plus x2 plus xn. Then I get n times mu minus n mu divided by n, which is 0. Right? So if I take the average deviation, it is 0. Now, why is it 0 intuitively? It's 0 intuitively because the mean is something like a midpoint, right? There are a bunch of scores that have a positive deviation from the mean, and they will exactly cancel out those scores that have a negative deviation from the mean. Why? Because the mean was decided as a balancing point in the middle. It was decided that way. So it's not surprising that the sum of all these deviations from the mean actually have to be equal to 0. Okay, so the problem there, is this clear what I just said about the deviations and how I'm getting this thing? Any questions anymore on this?
So,
I have
so
a
sir,
question.
sorry, go ahead.
Go ahead, just ask the question. One of you
Yeah.
go ahead.
So, sir, as per the definition, you said that x1 plus x2 till n is new. But when we see the on your screen, it is n new minus n new.
No, I
Ideally,
said x1
x1
plus
till
x2
xn
plus
you have
xn
already defined
divided
new.
by n is mu. So I didn't say x1 plus x2 plus xn is equal to mu. I said x1 plus x2 plus xn divided by n is mu. The average is mu.
Right. But like if you see the second last statement, it's n
Yeah.
mu minus n mu by n.
Yes.
So if we see this last statement, sir, already from x1 till xn we have defined as new. It's still n.
No. Yeah, x1 plus x2 plus xn divided by n is equal to mu, right? That's the definition of the mean. So all I did
Okay,
was
sir.
to say from the x1 plus x2 plus xn is now equal to n mu. So I plugged in n mu here.
Okay, sir. Okay. Straight. Yeah.
Okay.
Thank you, sir.
Yeah. Fine.
Anything?
Anything? Yeah. Go ahead.
Yes, sir. So here in x1 plus x2 plus xn divided by n is already
Yeah.
n mu, right? You're writing
No,
n
it's
mu
already
minus.
mu. No. It's already mu. Okay. See, the thing is, I think the real problem was that I should have interchanged the positions of equations 3 and 2. See, equation 3 comes before equation 2. Okay. We already know that the mean is given by this guy.
Yep.
Now,
I
equation
understood
3 is
that.
this. Yeah.
Yep.
Go
So
ahead.
once you divide it by n, it becomes n mu, right? So you get n
No.
mu
Once
minus.
you divide x1 plus x2 plus xn
Yeah.
by n, then you get mu.
Yeah. Right. Which
So
is
x1
which
plus
is
x2 plus xn will be n times mu, right?
yeah. So it is n
Yeah.
mu,
So
right?
n mu. So I put n mu
Yeah.
here.
Yeah, so n mu minus n mu by, you have written
By
that
n,
it is
yeah.
divided by n again, which is equal to 0. But you have
0,
already
yeah.
divided the n right before. So
So it's up to you how you actually handle this. So I have n mu in the numerator, again an n mu here. N mu minus n mu is 0. I can choose to divide n mu by n and n mu by n, and I get mu minus mu is 0. It's the same
okay,
thing.
got it. It's just a matter of representation, right? So
Yes,
we were
matter of
confused
representation.
about this
Exactly. Yeah.
equation. Okay, got it.
So, sir, the
Yeah, go
original
ahead.
problem we started is what we want to identify the average deviation, right?
Deviation, exactly.
And we concluded that average deviation is 0.
Is zero.
So is there a statement that we are in for any problem, average deviation would be
Yes.
0?
Yes.
Okay, great. Yes,
Any
thanks.
Okay. See, the problem was that this is a trick calculation. Okay. So I should probably not have done it this way. It's a trick calculation. See, the thing is, once you think about what the mean actually is, right, then this calculation should not come as a surprise. Why? Because the mean is a midpoint, right? And the midpoint was so chosen that all the positive deviations would cancel out all the negative deviations. And that's why the mean is the way it is. Right? If I move the mean a little bit to the right, then this calculation no longer be valid, right? Because then the positive deviations would be a little bit less than negative deviations, right? But the mean is so chosen that the positive deviations from a given number, which is the mean, is less than the negative deviation, is equal to the negative deviations from that same number. So positive, negative basically cancel out, right? So, but the idea of looking at deviation seems to be correct. The problem here was that I let positive numbers get cancelled out by negative numbers. So I could have, for example, a
sorry to
mean.
interrupt you.
Yeah, go ahead.
Sir, I just want to clear that, like, for the average deviation, it will be always 0.
Yes, will always be
Okay.
0.
Okay.
Because
Thank you,
this
sir.
calculation that I just did assumed nothing about the numbers.
Okay.
X1, x2, xn are arbitrary numbers. Any n numbers will always have this property. Okay.
Sir,
That's the
why
whole.
can't we?
Yeah,
Sir, sorry, sir. So why can't we take the mod of these numbers, like the spread, the delta?
That will also have problems. Okay, if you take the mode or the what do you call median or this sort of thing, then that will also have
No. Sorry, sir.
problems.
If I create a confusion. So what my point is, the modulus value of the difference. So when we say x1 minus mu, right?
Yeah. You're getting to the point.
Okay.
Okay, getting that will be one way of looking at it. Okay, see, we are going to pick a measure that will do something similar. We don't like to look at this sum of the moduli, the absolute values as you're talking about. That will do something similar. But the thing about absolute values is that sum is not very conducive to mathematical analysis. Okay, so sometimes we want to differentiate and so on and so forth. We want a measure that will also be differentiable. This modulus is not differentiable. Okay, so it's for some mathematical reasons we prefer not the measure you're suggesting, although it has the same spirit as what I'm going to suggest. It's not preferred in general. Okay, but you're on the right track to ask for that. So what we want is to not have
one
the
quick
positive
question, sorry.
deviations cancel out to negative deviations. Yeah, go ahead. Last question on this thing. Go ahead.
Sorry, so sum of deviations is always be zero, right? Then what is the average of
Yeah.
deviation?
So if the sum of the deviations is zero, if I divide that sum by n, I still get zero, isn't it?
That's right, yeah.
So the average deviation is still zero. What I
Hello,
showed
sir.
you was that the numerator is zero. So dividing it by n will also make it zero. Yeah, go ahead.
Yes, sir. So basically, this will always gives us a zero only. So
Yes,
what we are
yes.
trying to conclude with this equation?
What we're trying to conclude with this equation is that if you were to look at the average deviation from the mean, you'll get zero. So looking at deviation is fine. But if I were to take average deviation from the mean as some measure of spread, look, the reason why we got into this in the first place was to say we want to look at the spread of the distribution. So then we came up with, let's look at every number, look at its deviation from the mean and take the average deviation. That gives you some idea of spread, isn't it? I mean, naively. Right? Then we said, okay, but that average deviation computation fails because the average deviation is zero. Does this make sense as to why we were looking at deviation in the first place? Why we took average deviation? It was round one of an exercise to capture the spread of the distribution.
Yes, sir. Understood. Thank you.
Okay. And then we said that no, this is an inadequate measure because no matter what set of numbers you have, the average spread will always be zero. Average deviation will always be zero. But then one of you came up with this idea, instead of looking at positive guys canceling out negative guys, that's the crux of the problem. Why not we look at this? Okay. So one idea that we have, take x1 minus mu plus x2 minus mu as equal to average deviation. Okay, this is okay, but there are some problems in practice. There are some problems with this. Okay, to actually understand these problems and so on requires you to understand differentiation and other stuff. I don't want to go into all of that right now. Okay, so what we do is something similar. Okay, so take instead x1 minus mu squared plus x2 minus mu squared plus xn minus mu squared, right? And divided by n. This is average squared deviation. Okay, and this is called the variance. So this is a number that gives you an idea of the spread of the distribution, right? It's not going to be zero unless all numbers are focused on the mean. If I give you n numbers, miraculously all of them are exactly the same value, then the average of the set of numbers is mean, is mu, then the variance will also be zero. But for all reasonable distributions, the variance will be some finite number. And the more that number, the greater the spread of the distribution. So if I go back over to the original example that I had a while ago, where's this number? Yeah, look at this thing over here. If I were to take the average square deviation from curve 2, don't you agree that it will be greater than the average square deviation from curve 1? Because the mean is the same for both of them. I just have more points further to the right and further to the left in
Yes.
the second case, right? So the thing is, the variance will be more. So from our example, let me go over here. So let me redraw the example because you know what I'm talking about. And here, right? This is distribution 1, and this is distribution 2. Okay, this has more variance. Okay, so that number of square deviation is capturing something about the spread of the distribution, right? But then you might want to ask, okay, look, mean and variance are two numbers that describe the distribution, but does that tell you everything about the distribution? Okay, now the answer is no, because the distribution has a lot more information than just the mean and the variance. So I can think of, just as I constructed a bunch of data that had the same mean but looked very different each time, I can construct a bunch of data that will have the same mean and variance, but again keep looking different. Okay, so because I have many numbers to play with, right? You tell me the mean of some bunch of numbers has to be something, the variance of a bunch of numbers has to be something, right? And then I say, okay, if that's the case, I can play around with numbers, play around with the position of the numbers, have lots of numbers to play with. If you give me millions of numbers, I can play with them in a lot of ways to still have the same mean and the same variance, right? So the thing is, just two numbers, when you come to think about it, two numbers cannot do justice to the entire spread of numbers that you have, because that's a lot of information there, right? When you have n numbers, you have a lot of information. You're saying the first number is here, second number is there, etc., etc. How can you attempt to summarize all of that information with just two numbers? Okay, you're going to have to lose some information. So but the thing is, having the mean and the variance is still useful because it tells us something, some bulk characteristics of the data you get to know. Okay, okay, this is the mean, this is the general spread, right? And now if the distribution is Gaussian, then we can tell, okay, what percentage of the data will be between x minus mu and x plus mu. Oh, so sorry, mu minus a standard deviation and mu plus a standard deviation. But all that requires a little bit more about probability and so on. So I'll just want to leave it at the point where having knowledge of the mean and the variance is better than having knowledge of the mean itself. Okay, because you have some more idea of the shape of the distribution. So the purpose of a measure of variability is to describe the distribution and measure how well a measure of central tendency represents the distribution. Okay, you could have a certain mean and a very high variance. So what it means is that very few points are actually at the mean itself, right? The mean is the mean because there's lots of data with a large positive deviation, lots of data with a large negative deviation. It just so happens that they balance out at this point. That's why the mean is what it is. So mean, so if you, for example, look at it this way, if I have data that looks like this is a mean. And this is a huge variance. Okay. So that's telling you that the mean, if I have to look at the histogram, right, go back to that income profile thing, then you see that's a very unequal locality. Very few people actually have the mean income. Okay, it might so happen that almost nobody has the mean income. I can rearrange data to make that happen. Okay, nobody has the mean income, but this is the mean income, right? Mean income being a number doesn't mean that somebody actually has that mean income. No, it doesn't. It's just a number. It just averaged out all of the incomes and you got this number. It doesn't mean somebody actually has it. But the median income is something that somebody actually has, right? Because it's a sorted list of incomes and you pick the middle sorted income. So that's actually a real income of some living person, okay, in that list of numbers. So here's the mean. Nobody might actually have it. It's a number. So, but then you look at why the mean is the way it is. it turns out there's lots of people with pretty much zero income and lots of people with pretty much infinite income, right? Their average is here, right? So the mean, if I were to say that my country is this way, this is the average GDP, right? Or this is the average what do you call per capita income. But it turns out it's from a distribution that looks like this. That tells you pretty much nothing about how the average person is living in the country, right? Because it's just a number that happens to be there. But then if it so happened that the data looks like this, right? Like this. So this is your mean. And now there's very little variance, very little variance. So I don't need to know what the distribution of numbers is. I don't want to know their spread, but just these two numbers tells me something about spread. I don't have an actual knowledge of the shape of the distribution. That requires more information. Just the mean and the variance tells me something about how the distribution looks, what the spread is like. The second guy tells me if I applied it to a country and the incomes, right? It'll tell me that we have a very more or less equal country there. Okay, everyone earns the mean income. Whereas in the first case, you say that the mean income is pretty much meaningless, right? Nobody earns that mean income. That's the whole idea behind this thing. Okay, so the ranges are URL for Xmax and LRL for Xmin. So you take the smallest value and the highest value, and take the difference between those two, and that's some idea of the spread of the distribution. But it's not a meaningful idea. So the idea is that we want to summarize the data in a meaningful way from which insights can be drawn. If I just take the range, then the range can be arbitrarily large, right? Because it's decided only by two numbers. See, one problem with a measure, right? You have a lot of numbers and you're trying to get a single measure of that lot of numbers. So if two numbers in that lot of numbers were to actually decide that measure, then it's not a very informative measure, right? Because I could have a large negative outlier, a very negative outlier, and a very positive outlier, and those two are deciding the range, right? That's a one-sided picture. It's not telling you the whole story at all. So if you take something like the average square deviation, all the numbers in the data have a contribution to it. Okay, it has its own downsides as well, because when you're taking the square of numbers, one particular outlier can have a disproportionate qualification, a disproportionate contribution to the whole sum. So the sum will get distorted. And so if you were to summarize a lot of data with just one single number, distortions are inevitable. Okay, it's not possible for me to represent the integrity of a bunch of numbers with just a single number. But the average square deviation is still doing a reasonably good job in that it captures through a single number some sense of the spread of the distribution. Okay, so that's basically it. So what's the difference between the standard deviation and the variance? So basically, the standard deviation is simply the square root of the variance. Okay, so the most common and most important measure of variability is the standard deviation. It's a measure of the standard of the average distance from the mean. Okay, it describes whether the scores are clustered closely around the mean or are widely scattered. So the calculation differs for population and samples. Okay, so variance can be viewed as a companion concept to standard deviation, but it's not the same concept. The difference is that the standard deviation is the square root of the variance. Okay, so if you look at, let me go with this slide here. This is a standard deviation. So here's your mean mu. And if you look at this particular score, you see that the deviation is 5, right? If you look at this score, the deviation is only 1. Now, if I were to, like I said before, if I were to sum up all the deviations, don't power them to 2, just sum them all up, and then you get 0, right? So the average deviation is going to be 0. So this is what I just said about the mean being a balance point. We've already covered all of this stuff. So how do you find the standard deviation? You first square each deviation score, then sum the square deviations and average the square deviations. So the mean square deviation is the variance that I just showed you. I've covered a bunch of slides in a short while. Okay, so we're just summarizing all of that now. And the variability is now measured in squared units because it's the sum of squared deviations. The standard deviation will be the square root of that variance.
Sir, I have a
Okay.
question.
Yeah, go ahead. Go ahead.
Why it is always square? Why don't we consider cube or any other thing?
No,
Or maybe
cube.
raised to the power 4?
Yeah, but the thing is, raising to the power 4 and so on doesn't give you any particular what's it called advantages. Okay. See, the problem is that when I raise it already to the power 2, right? I allow for certain positive outliers to have a disproportionate contribution to the sum. That's one thing. If I raise it to the power 4, that problem will become worse. Okay. See, the original reason we wanted to raise the deviation to any power at all was to prevent negative deviations from cancelling out positive deviations. Right? That was the goal. Then one of you came up with a very good idea, which was to take the moduli of the deviations. That does that purpose. Okay. The moduli will ensure that you only take the absolute value of the deviation. So then when you take that, the sum is still giving you a good idea of the spread. But as I said before, there are certain mathematical reasons why we don't prefer this in all situations. Okay, having to do with differentiability, and so it's just not a very nice thing to work with mathematically. So the compromise is to take the power 2. If I take the power 2, I won't have a situation where one of the outliers will have a very high contribution to the total sum and distort it. Okay, I mean that there will be some distortion, but not quite as much as when you have power 4, 6, 8, 10, and so on. Okay, now what about having odd powers? Now, if I take odd powers like 3, 5, and so on, then I still have that positive negative cancellation going on in some way. A positive, say if I take 3 to the power 3, that's 27. Minus 3 to the power 3 is minus 27. Again, there'll be a cancellation. So 2 is like something like a compromise. Works reasonably well, doesn't create too much distortion, is easy to handle mathematically, etc., etc. Does this make sense? Why we're taking 2?
Yes, understood.
Okay, thank you. Move on. So the variance is sum of squared deviations divided by the number of scores. Thus, the sum of squared deviations is called SS. Okay, sigma x minus mu squared. So this, some of you might be unfamiliar with this notation. We'll use it significantly. This actually means sum. Okay, it's a Greek sigma symbol called sigma. So this is a Greek symbol called sigma. Okay, but this is the capital of this thing. This guy is also called sigma. It's like the letter small a and big A. Both are A. One is lowercase, one is uppercase. Same with Greek letters. Sigma, sigma, lowercase sigma, uppercase sigma. So this is the sum x minus mu whole squared. Okay. So the population variance equals the average squared deviation of scores from the population mean. And the variance is the average of squared deviations. So we identify the population variance with the lowercase Greek letter sigma, sigma squared. Okay, standard deviation is the square root of the variance, so that is the lowercase Greek letter sigma, small sigma, sigma squared. Okay, so here's a few examples of how this is going on. You have that data that we saw for a while ago. If I take the average, is the sum of all of these guys, 2 plus 8 plus 5 plus 3 plus 7 plus 8 plus 5 plus 2 plus 5 divided by 9, that's still 5. You can verify it for yourself. And now look at what we have done over here. I'm taking the standard deviation to be sigma x minus x bar the whole squared. That is the sum of square deviations. And I'm dividing it by something, right, and taking the square root. Now, if I keep this slide on for a bit longer, I expect to get a storm of protest from all of you saying you said that you should divide by n. Is it a typo that we're dividing it by n minus 1? Okay. To preempt that storm of protest, I'm going to tell you that this is no typo, not a typo. We actually mean this.
This is for sample, right?
Yes. Okay. Yeah, it's a sample. So if you already have some background in this subject, see, the thing is that, okay, let me just give you an idea as to where it comes. I'm not sure if we do it in this slide itself. Yeah, okay, we do it in this slide. So let me just explain to you what's going on from one note. I did. Okay, let's look at it this way. There is such a thing as a population mean. right? Now, let's say you have a very, very large amount of data. Let's say the country's population. Right? Has a mean income. Right? Now, the thing is, in order to actually calculate this, mean, right? We need to look at every single score, every single income in the country. Not possible. Okay, so the population mean would be a nice thing to have, but it's not possible to get. So what do? We draw a sample of incomes from the population. Okay, can you please go off onto mute mode, whoever it is? So the sample is say n samples. Right, and then say, look, you want me to estimate the statistics of the entire population. I can't do that because it's just too time consuming. What I'm going to do instead is to draw some 1,000 people out of it, right? And estimate statistics the whole population from this 1,000. Okay. Now, immediately, some of you are also going to protest. How do you know that the 1,000 people that you are sampling are truly representative of the population? Okay, the population has 25% old people, 25% young people, the 5% unemployed people, etc., etc. In some proportion, it's a very complex population, right? And that's why these statistics have to be computed. It's a complex population. There are unemployed people, there are old people, there are young people, there are sick people, there are very rich people, there are NRIs, there are residents, etc., etc. And the whole income thing is going to be a totally difficult number to calculate. So if I take a sample, the 1,000 people I take, or whatever number n I take, right, must have pretty much the same proportion of the same category of people as in the general population. So if I have 25% of the people in general population as being old and who are therefore not earning or probably earning a meager pension, then I must have 25% of these n people in the same category. How are you going to ensure that? Well, then there's a question of how do you sample in a scientific way, etc. It's a whole different kettle of fish. I'm not going to go into that. I have just a set of n samples. Okay, I'm not going to talk about whether representative or not. But what I'll do is I'll calculate sample mean as x1 plus x2 plus all the way up to xn divided by n. Okay, and say we pretend going to highlight pretend the sample mean is equal to the population mean. Okay. Now the thing is that's not going to be the case anyway, right? But then suppose I say I want to estimate the population variance also. So what I do is I say, look, the only data I actually have of the population is my sample, nothing else. So I create, let's say, a possible measure of variance is equal to x1 minus, what did I use there for sample mean? Let's call this x bar, okay? Just to keep the same notation as in the slides. This is the mu that I was talking about previously, but mu I'm going to use for the population mean. This is a sample mean, okay? So I have x1 minus x bar the whole squared plus x2 minus x bar the whole squared plus all the way up to xn minus x bar the whole squared, and I'm going to divide this guy by n. Okay, this looks like a natural formula. Okay, but it is flawed. Why is it flawed? Well, the thing is, the sample has less variability than the main population, than the whole population. So when you look at this numerator here, right, x1 minus x bar squared plus x2 minus x bar squared plus xn minus x bar squared, then you say that there's something wrong with this computation. It is that x bar already is used to the data. See, the thing is, x bar was computed from the data, right? X bar is equal to x1 plus x2 plus x3 up to xn divided by n. So the thing is, x bar already sits bang in the middle of all of the data. Whereas the population mean might actually be quite far away. Right? So if to show it graphically, if I have x1, x2 up to x, this is what I actually collected. Okay, this is on sample. Right? This is a sample we collected. Sample we collected. And where is x bar? X bar is here. It sits somewhere in the middle. Right? Now, if I take x1 minus x bar the whole squared plus x2 minus x bar the whole squared plus so on and so forth, xn minus x bar the whole squared, and take just let's take the sum here. Don't divide by n right now. Okay, if you take this sum, it might not be all that high. All that high. Right? Because this x bar already has some knowledge of the data, right? It has located itself in the middle of the data. Let's say the actual population mean is here. Okay, actual population mean. It could be, right? I could have had an unrepresentative sample. If I had an actual unrepresentative sample, the population mean could lie anywhere, basically. Let's say it lies further to the right of the largest guy over here. Then if I take x1 minus mu the whole squared plus x2 minus mu the whole squared plus xn minus mu the whole squared, right, and divide by n, that is a different measure of a mean, right? The average square deviation. But I don't have access to that mu, right? I use data already to compute x bar, and I'm using that x bar again. So what has happened is some kind of overfitting has happened to the data. The x bar that I'm using in the data somehow fits the data better, right? So x1 minus x bar, so x1 minus x bar the whole squared plus xn minus x bar the whole squared will generally be less than x1 minus mu the whole squared plus xn minus mu the whole squared, where mu is population mean and x bar is sample mean. Okay, this will generally be less because x bar is sitting bang in the middle of the data, whereas mu has no such restriction, right? So the thing is, it turns out that we can compensate for this. We can compensate for this in a mathematically correct way. Okay, now the question is, what is mathematically correct way? I can't tell you yet because we don't know what are the expectations and so on, right? It's coming up in later in the course. So I'm just going to leave this as a placeholder. It turns out that we can compensate for this in a mathematically correct way by dividing the smaller x1 minus x1 bar squared plus xn minus x bar squared by n minus 1, not n. So we're dividing by a smaller number, n minus 1. Okay, not n. And when we do that, magically, there is some kind of, like I said, mathematically correct way, right? There's a compensation that's happening. The calculation does not have any bias. Okay, but to understand the notion of bias, etc., I have to talk about expectations and so on. We have, like I said, that's yet to come in this course. So it's not a typo, basically. Okay, the thing is the numerators that doesn't reflect the sum total of squared variability that you expect to have if you actually use the population mean. I don't have the population mean, so I have only sample mean, so I do this. Okay, and this is my by standard deviation.
Sir, I
Okay,
have a
so
question.
go ahead, go ahead.
Sir, the explanation what you gave that very
Yes.
well fits for a large population. But in the previous slide, it was only 10 observations or 10 data points. So for
No,
that also, is that
yeah.
necessary?
No,
Yeah.
no. The thing is that this was a sample from population.
Okay.
Although this is not the whole population. If this was the whole population, then what you say is correct.
Okay.
But what I have is only a sample. See, the thing is, we don't always make it very clear as to what we're talking about. Okay, so when we take only say a few points, then we assume that this comes from a larger population. So this whole statistics becomes necessary because the setting is that you have a large population, right? If I were to actually truly go and calculate the mean of the population itself, then I can do S is equal to sigma x minus mu squared by n, right? No issues at all. And take the square root of it, that gives me standard deviation and stuff like that. Because I'm talking about the whole population. But then if I were to have a whole population that simply is too large for me to work with, then I have to work with a sample, a small sample out of it. So when I take a small sample, then this is the adjustment I have to make. So in answer to your question, you pretend that the data on the left-hand side is sample data, not the population data.
Okay, and this formula that standard deviation is square root of variance that holds for any data, right? Standard deviation
that holds.
is
It's square root of variance holds for any data. It's just that variance is being computed, keeping in mind that we are working with a sample rather than the population. So if we had been working with the population, then the variance formula would be sigma x minus this x bar would be mu instead of x bar. So it'll be sigma x minus mu the whole square divided by n. If we know that we're working the population, since we are working with a sample, it's sigma x minus x bar the whole square divided by n minus 1.
I was just in one doubt that our variance was summation of all the squares and divided by
the
n.
number.
Divided by the number. So ideally, standard deviation, now the square root when it is happening for standard deviation, it is happening. We should take the square root only for the numerator, right? But by n also it is getting.
No. The thing is the numerator.
That was what
the
doubt.
Numerator by itself doesn't represent. Numerator by itself doesn't represent a statistically useful quantity. So if I take sigma x minus x bar the whole square divided by n, let's forget about the n minus 1 business for now. Okay. Then if I do sigma x minus, suppose I take sigma x minus mu squared divided by n, that is the average. Okay. Now, okay, let me just give you an idea as to why we do what we do. It's a good point. Let me just go get over here. Add a page. So your point was if I take sigma xi
why
minus
we are taking the root of the denominator?
One sec. Suppose we take this, okay? And if I take square root of sigma x minus mu the whole squared and divide by n. So now the thing is that this guy over here is the average squared deviation. And now we're taking the square root of the average square deviation. Whereas this guy over here is equivalent to square root of sigma xi minus mu the whole squared divided by n squared. Right? Now, what what meaning can you ascribe to this quantity under the square root sign? What meaning does this have? It is a number, all right, but it's hard to identify what kind of meaning it has, right? Why are you dividing sigma x minus mu the whole squared divided by n squared? I mean, so what? You see where I'm getting with this, right? See, at the
Yeah,
end of the
yeah.
day, it's mathematics, it's formula, so I can write anything I want, and it'll have some meaning. But the thing is, can we understand what that means? So it's much better to talk about the average square deviation like this, and then take the square root.
Yes, sir. Makes sense. Thank you.
Sir, I have one doubt.
Sir,
Yeah,
I
go
have a
ahead.
question.
So in the mean, you have taken uh, the summation, and after that you are dividing with the whole number of like sample data set.
Yeah.
But you in a standard deviation you have taken the sample number like n minus one,
sample mean,
and in the
yes,
mean you
yes.
have taken the total number. Why
Yeah.
is that? We have to take the sample mean sample number, correct? That's an
Yeah. So the thing is, this here I just used as the population
no,
mean.
in the slide. Can
Yeah.
you go to in the slide?
In the slide or the OneNote?
In the slide.
Slide. Okay, let's go to the slide. Okay.
Yes.
Yeah.
In the mean, so you have taken the summation of xi after you divide it with the capital N. That's
this
a
is
total
fine.
mean.
So yeah,
Total.
so the thing is, this x bar is not biased now. See, the problem is this. Okay, when I compute x bar is the first number I'm computing out of the given statistics. Okay, that is the mean.
Correct.
And that is computed in a bias-free way, even if I use n here. In fact, I have to use n here. Okay, see, the thing is that the reason when you go from x bar to s, there's a difference that comes in. It's because I'm already using something out of the given statistics and I'm reusing it. So bias comes in because of that. When it's something like this. Okay, suppose I have a lot of data. These are raw data. I apply a first level computation on it. That's x bar. Now to do x bar, I can actually take x bar is equal to the sum over all of the xi's and divide by n. And then there is no problem with that computation because all the data was used in raw form for the first time. Okay, so that so x bar is essentially an uncorrupted measure of the population mean. Okay, if I take the sum of all of the sample guys divided by n, I get the population mean. Well, sometimes I get the population mean is to the right of it, sometimes it's to the left of it, etc. But in statistical terms, it's an unbiased estimate of the population mean. Okay, that's x bar. The problem comes in when I reuse that x bar in the second computation. Even if x bar was computed in an uncorrupt way in the first computation, reusing it in the second computation to compute the population variance is introducing a certain bias. Why do you have a bias? It's because x bar is being reused in the computation. Already data was used once to compute x bar, right? So that x bar is now fitting that data. And then when you take what do you call the sum of squares, square deviations, then because you're using x bar instead of the population mean there, some bias crept into the computation. It's because that x bar is being used again, right? It's not an independent assessment of the data anymore. When you have x bar computed the first time, that was an independent assessment of the mean of the data. But when you use that x bar again to compute the sample variance, right, then you no longer have an independent assessment of the data. Okay, that x bar already fits the data. Whereas if I had used mu, the population mean there, right, then I don't know what mu is, right? Mu has no real connection to the sample that I have chosen. Whereas x bar does have a connection to the sample I've chosen. X bar is decided by the sample I've chosen. So x bar is not independent of the sample I've chosen. So that's why to fix that lack of independence of x bar in the second computation, I have to divide by n minus 1. Does this make sense, at least intuitively? Because if I have to describe it properly, I have to go into a fair bit of math. I'll do it eventually, but that will come in some later lecture.
Excuse me, sir.
Sir, why we are taking n minus 1 instead of n?
Yeah, that is to account for the bias of the computation. See, there is a sample. Let's look at the big picture, okay? I'm not going to go too deep into it, like I said, because I need a lot more math than I can assume as background right now. So we have a sample. Okay, we computed x bar. Okay, X bar is an independent, so let's say not use independent, is an unbiased estimate of the mean. Unbiased estimate of the population mean. Now we use this X bar in computing the variance. So if I do sigma xi minus x bar the whole squared and divide by n minus 1, this n minus 1 accounts for bias due to the use of x bar instead of the population mean, which is mu.
Sir, is it always n minus 1 or dependent on some other?
No, it's always n minus 1.
So thing is, like, suppose if in the first one we are using X bar as in sample only, but but X bar is equal to mu only, right? If we are not like going to the
X bar is
variance.
not equal to mu. Okay,
No,
X bar
so
is
if
an
we are not taking a
unbiased
sample,
estimate.
yeah. So from the whole population, we are making a sample and we are doing all the stuff on it, and then we are predicting it, right? So in a zoom out way, I feel X bar is equal to mu only in the first glance. What I'm getting at. But
So
when
the
we
thing
are
is, hang on. See, the thing is, you people are forcing me to spill the beans. Okay, see, with your intuition is correct. Okay, it's not that it is not that x bar is equal to mu. Not that x bar is equal to mu. It is that expectation x bar is equal to mu. Okay, no bias in x bar.
So
in other words, let me just finish this point. In other words, basically what is happening is that, let's say this is your entire population. Okay, and X bar was computed from this guy, this guy, this guy, and this guy were chosen in your sample. Okay, 1, 2, 3, 4 was chosen in your sample. So X bar is X1 plus X2 plus X3 plus X4 divided by 4.
4.
Okay, let's say the sample mean, the population mean is this point here, mu. So then what I'm saying is that if I were to take this X bar, right, then it will so happen that X bar might be a little bit to the left of mu. Because after all, it's just a single sample, right? I took a single sample. I don't know where it came from. I took the average of it. That's X bar. And it turns out to be to the left of mu. Let me repeat that experiment by drawing another sample. Okay, then it might so happen that the X bar computed out of that sample is to the right of mu.
Can you give me give some real time example? I mean to say from calculation point of view so that I can understand it.
Okay, fine. Let's
Actually,
work with the income
it.
example. Let's work with the income example. Let's take the average income of everybody in the country. Okay, so what I'm going to do is, if a person is earning nothing, if a person is a child, income is 0. If a person is a old age person with or without a pension, if it's with a pension, the income is the pension. If it's without that pension, the income is 0. And so every single person, man, woman, child, baby, etc., has a number associated with their name, right? That's their income. I take the average of all of that, right? The whole country's population's average income is some particular mu, right? Fine. Now I draw 100 people, some 100 people. 5 are from Bengal, 8 are from Bihar, 10 are from Karnataka, etc., etc.
Are you drawing
That's
somewhere?
a sample. Huh?
Are you drawing somewhere?
No, I'm not drawing
or
anywhere.
It's
I'm just explaining. I'm just explaining in words. Yeah, I'm explaining in words. Okay. So you draw 10 people from different states, right? Then you construct a sample. Now that sample has an arbitrary number of old people, young people, high income earners, etc., etc. Right? Like I said, don't ask how I'm getting a representative sample. That's a story for another day. I got a sample. I've computed X bar. Right? So what I do is, in the sample, I just do something like this. Like I to construct a sample randomly, I just throw darts. Okay, I assume that the country's population is on one big line. Then I say, okay, I'm going to generate a random number between 0 and the size of the country's population. Whatever that random number is, I'm going to pick the index associated with that. So maybe I'm talking too much now. So instead of hand waving, let's do it this way. Let's say 0, and this is the country's population. Imagine that I have the country's population like this, and I put every single person standing in line. Okay, standing in line. Everyone standing in line. Then how do I create the sample? Well, I don't toss a coin. Well, I don't, or let's, so I generate a random number, a uniform random number. Between 0 and size of country's population. So this right hand number is the size, okay, size of country's population. So that number will could be this guy, or could be this guy, or could be this guy, or could be this guy. It all happens with the same chance. Okay, with a small chance it's this guy, with a small chance it's this guy, with a small chance it's this guy. Okay, and so on and so forth. So there's no bias in that number. Wherever that number falls, I'm going to pick that person. That guy goes into the sample. So I do that experiment 100 times. Okay, now each time I do the experiment, I can in principle choose the same guy again because it's a repeated sample. Okay, the same guy can, with a very small probability, the same guy will come back again in the second try. But let's ignore all that. So like this, I draw 100 samples. Okay, so 100 people are created into my 100 people are loaded into my sample, and I take the average of these 100 people and so on. This is what gives me X bar. Okay, now where is X bar going to be with respect to mu? It can be anywhere, right? If I did this process, mu is some number, X bar is some number, etc. Now, if I do this experiment repeatedly, so in the first experiment, I draw 100 people at random from the country's population, take their average income. That's X bar. In the second experiment, again, I draw 100 people from the country's population. Again, I get X bar prime, a new X bar, then X bar double prime, right? So first, between 0 and country's population, and pick that person from the country's population, and add to the sample. Okay, so create a sample of n people. The next page. Create a sample of n people. Compute X bar. Compute X bar is x1 plus x2 plus xn divided by n. Repeat the experiment. A new sample of n people. Then you get X bar prime is x1 prime plus xn prime divided by n. Right? And then keep doing it. Now, what we can say is that each X bar need not be mu. Okay, but expectation of X bar will be equal to mu. So it is unbiased. By expectation, what I mean is that if I take the average of all of the X bars that are coming out of the experiment, the first 100 people, n is 100, the first 100 people, I got an X bar. Then I put all the 100 people back into the sample, back into the country's population. I redid this experiment. I got another 100 people, some of whom may be the same as the guys before. I don't care. I get X bar prime. Then I get X bar double prime. Then I get X bar triple prime and so on. If I take the average of all of those X bars, right, and I do the experiment an infinite number of times, I take the average of all of those guys, that number will be mu because of the sampling process.
What is in this case is a X bar? X bar means the average of
Average
all the.
income of the 100 people that you have selected.
Okay.
So, sir,
X
if you're
bar.
Sample
So
mean.
X
The
bar.
average of the average is likely to be the population mean.
You mean to say that is a X bar, right?
Yeah, this X bar is the average of the average income of the n people in the sample.
And what is X?
So X bar, so X is a particular person, right? So it's like this. You have out of X1, X2, Xn, right? This is a bag consisting of a sample, right? Out of this guy, you have created X bar. This is the X bar. And I'm saying that if I have, this is sample 1. Second, what's going on? Why can't I go down, go below? Yeah, here we go. So here, so this is X bar, one sample. Now, if I draw another sample, I get X1 prime, X2 prime, Xn prime. This will give me X bar prime, another sample. Then I do X1 double prime, X2 double prime, Xn double prime. Will give me yet another sample. So now you have a sample mean, right? That is X1 plus X2 plus Xn divided by n. That's what's its relationship to the population mean. It could either be to the left of it or the right of it. If I take X bar prime, again, it's another sample, another sample mean. So it could again be to the left or right of the population mean. Now, because of the way we are drawing this sample, you can say eventually that the average of all of these sample means, right, will be like mu. Okay, so the thing is, although your individual sample has a unknown relationship to the population mean, the fact that you're repeatedly doing this experiment in an unbiased way, right, means that if I take the average of all of these guys, I will get more or less the population mean. Okay, so when I use the raw data to compute x bar, I can divide x1 plus x2 plus xn divided by n and get x bar. There I can divide by n. But when I use that x bar again, then that n becomes n minus 1. The real problem is the number of degrees of freedom that you have. So when I compute the sample mean, I have n degrees of freedom because I'm using raw data for the first time, right? Then when I compute x bar and I reuse that in the second computation for the standard deviation, I lose 1 degree of freedom because 1 degree of freedom has already been consumed by x bar. Because x bar has been computed out of that same data itself, right? And you're reusing it so that you lose a certain degree of freedom. The answer that you get has an inherent bias in it because x bar has had a chance to fit the data, right? The population mean and the sample mean that you have uh, 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 are unrelated. The population mean can be anywhere. But if I take the sample mean has to be bang in the middle of all the sample data. It has no place else to go. Right? Whereas the population mean could have been to the right of this, could have been to the right of xn, could have been to the left of x1, could have been somewhere in the middle, could have been anywhere. But the moment I use x1 through xn to compute the sample mean now has a relationship to the data. It can't lie anywhere. So you have lost a degree of freedom. To account for that in the mathematical way we do and divide by n minus 1. So that explanation I'd like to move on. Okay, it might not be totally satisfactory, but I hope some of you have got an idea of what I'm talking about. A proper mathematical treatment of this will be given when we talk about expectations and so on. That will come a little bit later. Is that fine?
Yes, sir. So on the slide, it will be expected X bar, right? Instead of only X bar.
No, this will be X bar. Expected X bar means that you're taking multiple samples of this kind. and
Then
taking the average
this
of them.
capital N should be the small n, no? Like in a whole sample, the main sample, we are having the complete population, which is represented by the capital
Yes.
N. Then we are taking
If
a
you
small
have,
sample up
okay,
out
look,
of it.
let's keep the terms fixed. Okay, this n is the sample size. Okay, I'm assuming implicitly that somebody has given me a sample out of a larger population. I don't even know what the larger population is. They gave me a sample consisting of these 9 items. I'm computing sample mean this way in this slide. It has
Got it. So
nothing to do with the
in
population
this,
mean.
yeah. So in this, like this table, that numbers we have, that is a sample space, right?
Yes,
That's
that's a
sample,
sample. Yeah.
right?
This
So
n should
which is
actually be
represented
big
by, yeah, it should be the bigger and then yeah.
N. Big N. There's no small n. That's just a typo. Okay, so in the interest of course coverage, we are actually we're supposed to be in lecture 2 at this time. Okay, so I'm going to go a little bit faster now. Okay, so the standard deviation and the variance for a sample, the goal of the inferential statistics is to draw general conclusions about population based on limited information from a sample. Okay, that's the whole problem. The samples differ from the population because samples have less variability. Computing the variance and standard deviation in the same way as for a population would give a biased estimation of the population values. So the thing is, this is admittedly a hand-waving description right now. The reason it's hand-waving is because we don't have sufficient background to go into a deeper level. Okay, but eventually I will do it. So the sum of squares is computed as before. The formula of the variance has n minus 1. This is actually n minus 1. Okay, not small n minus 1, rather than n in the denominator. Okay, so the variance of sample becomes s squared is equal to ss divided by this n minus 1, and the standard deviation becomes square root of ss divided by n minus 1. So the n minus 1 comes to account for that bias because you're working with the sample data, because x bar was used to compute that sample data, and now you're using that x bar again. And the reason you're using that x bar again is you don't have access to the population mean. Okay, that's the whole thing. Okay, so we're pretty much done. So the rest of this is a bunch of practice problems and so on. But there's a little bit more of theory. I'm going to look at this and go to that theory. So a sample of 4 scores has SS is equal to 24. What is the variance? So the variance will be 8 because it will be 24 divided by 4 minus 1. This 4 is equal to n. Okay, so the trick here is that because it's a sample of 4 scores, okay, and if they're asking you what is the variance, you have to use n minus 1 rather than n. Okay, so that's why the variance is 8 and not 6. Okay, so a sample systematically has less variability in the population. Yes, it's true because a sample has fewer elements in it. The standard deviation is the distance from the mean to the farthest point of the distribution curve. No, that's not true. Okay, because it is the average deviation, average square
Sir, what
deviation,
is
not
this
the deviation.
SS?
SS is this sum of squares. Okay, sum of squares of those deviations. Okay, that is sigma xi minus x bar the whole
Understood,
squared.
sir.
Yeah.
Could you please
Okay.
explain the last one, the B?
B, okay. The standard deviation, the distance from the mean to the farthest point on the distribution curve. That's not true, isn't it? Because you took the average of the square deviations. It's not the distance to the farthest point. It's an average deviation.
Yeah, okay.
Okay,
Thank you.
okay. So descriptive statistics basically means that you describe an entire distribution with just 2 numbers, m and s. Okay, so the reference to both allows reconstruction of the measurement scale from just these 2 numbers. The means and standard deviations together provide extremely useful descriptive statistics for characterizing distributions, but as I have been emphasizing so far, they are not sufficient. Okay, because you can't just use 2 numbers to describe a much larger set of numbers. It doesn't work that way. Okay, there will be some information loss. So the entire shape of the distribution cannot be restored by just knowing mean and variance, but you can still answer some useful questions about it. Okay, now there's something called a 5-point summary of data, which says if somebody gave you a data of n items, right, then how do you actually identify the 5-point summary of that data? You have the minimum, Then you have the Q1, the first quartile of the 25% mark. Then you have the median. Then you have Q3, the third quartile of 75% mark. And then you have the maximum. So if you want a 5-point summary of the data, you ask what is the smallest element in the data? What is Q1? What is that point that marks that point in the data such that 25% of the data is less than that point, and 75% is more than it? That's Q1. Okay, that point is called Q1. Then there's a median. That's basically Q2, the second quartile. 50% of the data is less than this point. 50% of the data is more than this point. Q3, the third quartile, 75% mark. Then then there is a maximum. So this, if you look at these 5 points on the data, that tells you a fairly good idea as to how the data is spread, how much mass is there in these different segments, and so on. It's not the whole data, but it is a summary of the data. It's a 5-point summary of the data. Okay, so there's also something called the interquartile range, which is the distance between Q3 and Q1. Q3 minus Q1. Okay, it's the mid spread, spread in the middle 50%. So you can view the data like this. This is the minimum point. This is Q1. This is median. This is Q3, and this is max. So you're asking, okay, 25% of the data is less than this Q1. 75% of the data is less than this Q3. So how much data is here? 50% of the data. Okay, so you're asking, if I look at the interquartile range, Q3 minus Q1, that tells you how much data, 50% of the data lies between this Q3 and this Q1. So that tells you something about your distribution of data. Okay, so that's interquartile range. It gives you the range that contains 50% of the total data. Okay, the best way to look at this is through an example. So we have a data in an ordered array, okay, 11, 12, 13, 16, and all the way up to 21. So then we look at, one second, we look at position of Q1. Now we say 1, okay, times, because we're taking the first quartile is basically 1 by 4, times the average position. The first guy is at position 1, second guy is 2, 3, 4, 5, 6, 7, 8, and this is 9. So 1 plus 9. Okay, that gives you the position of Q1 is 2.5. That is, you have to go 2 units and half a unit to the right. Okay, so 2.5. Now, what element is there at the 2.5 position? Well, you assume that there is a 12.5 over here. Okay, so what you're doing basically is that if Q1, the position of Q1 turns out to be some non-integer like this, so you say, okay, what is in position 2, plus you interpolate. So the value that of Q1 is, can be viewed as 12, what is in position 2, plus what is in position 3, 13. 13 minus 12 times this, because it's 2.5, right? You take 0.5 here.
0.5.
Yeah. So 12.5. Now, that's one way of looking at this quartile thing. Okay, it's basically a positioning type of thing. As you can imagine, there are multiple different definitions of it. You can also say that let me identify the median of this data, and that is Q2. And then I go to the lower half of the data and find the median of the lower half, and that will be Q1. That's the median of lower half is Q1, the median of upper half is Q3. Okay, that's another way of looking at this these quartile statistics. You won't get the same results as this one. It's just a different interpretation. You can take it that way as well. But what we are talking about in these slides follows this formula. Okay, so if, for example, what would be the median of this data? It would be so it would be, okay, between 16 and 17, right? No, not between 16 and 17. 1 second, where's the eraser? So the median will be 16, because there are 4 elements to the left of this, 4 elements to the right of this. Because it's odd number data, this is the median. Okay, then you take the median of the lower half of the data, then the lower half of the data 11, 12, 13, and 16. then the median will be, because now that you have an even number of elements in it, the median will be between 12 and 13, so it's still 12.5. In this case, you get the same result. But in general, you might not get the same result as this. So anyway, this is in our positional quartile definition, you first calculate the position of the quartile, then actually use the interpolation to find out the actual value. So we did that. The position is the 2.5 the position between 2 and 3. So that's 12.5. Then for position of Q3, it is 3 by 4 times 9 plus 1. Why do you get 9 plus 1? 9 is the last position, 1 is the first position, 9 plus 1. Okay, 3 by 4 into 9 plus 1 is 7.5. Okay, so interquartile range is Q3 minus Q1, 17.5 minus 12.5, which is 5. Okay, then you have the quartile deviation, which is half of the defined as the half of the interquartile range. Okay, so that's just a statistical thing. Now you can put all of this data together and form what is called the box and the whisker plot. And this is the diagram is self-explanatory. So basically, right? So you identify min, then you identify max, and then you identify Q1, Q3, and Q2. Okay. Now Q2 doesn't actually have to be between Q1 and Q3 because Q2 is a median position. Now Q1 represents 25% of the data is to the left. And Q2 represents 50% of the data is to the left. Q3 represents 75% of the data. Right? So we know that 25% of the data sits here. Right? And we know that a further 25% of the data sits here. But the spread of this 25% of the data need not be the same as the spread of this 25% of the data. Right? The number of data points is the same, but the spread is different. So that means Q2 can be somewhere over here, not bang between Q1 and Q3. Okay, because we're talking about the median, not the mean. Okay, so this is Q1, this is Q2, this is Q3. Then you have Q1 minus 1.5 times IQR, Q3 plus 1.5 times IQR. The reason you want these two guys is that you want to have some measure of outliers. So you say that any point that lies to Q3 plus 1.5 times IQR to the right of that, that's an outlier. So most of the data lies between Q1 and Q3, 50% of the data, right? Between Q1 and Q3. So Q3 marks out 75% of the data. If I add a little bit more to it, 1.5 times IQR, and look at the right of it, then I call those point outliers. Okay. If I had to just describe data to someone, give a summary, then I can use this kind of a description. Okay. It's a purely sort of arbitrary type of a thing, which nonetheless gives you some idea of the distribution of the data. Then you can also talk about major outliers that lies on to the right of Q3 plus 3 IQR and Q1 minus 3 IQR. Okay, so that's basically it. Then, okay, the rest of it is practice problems, which you can look at for yourself. Okay, I'm not going to spend time on this. So let me go into the theory of lecture 2. Okay, so I don't want to spend too much time in doing practice problems. They're self-explanatory to a large extent.
Sir,
Okay.
you are going too fast.
I'm actually going too slow. No, I'm answering your questions, right? So if you have any residual questions about lecture 1, please get in touch with me on email or so I try to answer those questions. But is there any last question you have on it?
So why this median is not between Q1 and Q3?
That's because the median respects only position of data, isn't it? It doesn't respect where the data actually is. So you could have data like this, isn't it? If I have a highly skewed distribution, let's talk about this. If I have a highly skewed distribution like this, where is the 50% of the data? It could be somewhere here, isn't it?
Yes.
And where is the mean? Mean will be somewhere here. So median reflects ranking of data. So if I say the median is 50%, right, that means this is the point where such that 50% of all of the given data is to the left of this point and 50% to the right of it. Now the 50% to the left of this point can be highly bunched very close to each other, right? And the 50% to the right of this point can be spread out. That will make the median look look to be positioned in an asymmetric way. It's all about ranking 1, 2, 3, 4, 5, 6 up to 50. The 50% point. Half of the data is to the left. Who is saying anything about how that data is bunched? Half of the data is to the right. Who is saying anything about how that data is bunched? It's just the halfway point, the ranking. That's it. You have a competitive exam. Somebody got the median score, right? Now, what is the relationship between the median score and the mean score? The mean score can be pretty high, isn't it? Because like if you take JEE Advanced, for example, the topper will be an outlier. He'll be somewhere here. There'll be about, if I look at the 50%, if I look at the mean, right, the mean will be somewhere here. Mean of JEE Advanced. But if I look at the median, that'll be further to the left. That's why it's somewhere here. Because the score that 50% of the candidates could not cross is a pretty low score. Okay. And although 50% of the candidates did cross this score, a large number of them were only slightly above it. Then there were a few outliers. One guy effectively got all the marks in the exam. That guy is pushing the mean to the right. Does that make sense?
Yes, sir.
So let me move on then, session 2. Now, what we want to do in this session is to look at axioms of probability. Okay, so we slowly want to formalize a lot of these notions, right? So I want to talk now about probability, axioms of probability, then we can get to expectation and so on and so forth. So we look at axioms of probability, mutually exclusive and independent events, problem solving, and so on to understand basic probability concepts. So let me move on here. Okay, so what is this notion of a random experiment? Let's talk about the notion of a random experiment. So a random experiment is something like this. Suppose you flip a coin. Did it land with heads or tails facing up? Now here you have a coin, right? Let's assume now that you have a coin, and when I toss it up, it goes up to a certain height, it twirls in the air, goes up to a certain height, and then falls, right? Now, it is common to say that we could get either a heads or tail, right? Heads or tails. We don't know what we would have got. So the experiment is random for all practical purposes. But then you can say that suppose I knew what was the launch velocity of the coin, how many twirls it does. I have the physics of it completely nailed up. Okay, I know how many times it twirls. I know what the height is that it goes to. Then I know how many twirls it will make on the way down. So in principle, I can actually calculate what it will land on. I know how high it would have gone. I know what distance it would have to come down from there. I know how many twirls it makes on the way because I have the physics completely nailed. Right? And then the outcome becomes deterministic. Right? Get my point, right? If I know enough about the physics of the process of tossing a coin, then it's not a mystery to me as to what outcome I would have actually got. But if I don't know the physics, then I can pretend that the whole thing was completely random. So a random experiment should be viewed in quote unquote. It's random because we don't have complete knowledge of the system. Okay, not that the outcome itself is truly random. So I'm bunching together situations where the outcome itself is truly random. Maybe there are certain things where the outcome itself is truly random. But most natural processes, once you know enough of the physics that's behind the generation of the natural process, you can say it's no longer really random. Okay, so the thing is, it's all about interpretation here. I'm saying that you have a coin that's being flipped. We don't have enough knowledge of the physics of the coins. That's why we claim that we don't know whether it would land with heads or tails up. So that's why we say it's a random outcome. Now, you walk to a bus stop. How long do you wait for the arrival of a bus? That's a random number too, from your perspective, right? Because you don't know how many buses that are running on that route, whether the buses were all started on time on a given day, whether there are any disruptions along the way, and so on. So, in other words, the randomness of events is really, in many cases, a cover up for ignorance. Okay, so I just want to emphasize that randomness of an event is a cover for a lack of knowledge of the event. If we knew the physics of tossing a coin, we could, in principle, calculate the outcome, right? It would then be deterministic. But if we don't have that, then we say lazily, right? It's a random thing. So give a lecture, how many students are listening? Well, this is also deterministic, actually. Although I can't tell in this particular case how many of you are actually listening to me, but it's possible to, in each of these cases, with a lot of knowledge, it's possible to actually compute all of this stuff. The other examples also, that they transmit one of a collection of waveforms over a channel. What waveform arrives as a receiver? So we treat that as if it's a random number. We don't know, right? You transmit one of a collection of waveforms over a channel. Which waveform does the receiver identify as the transmitted waveform? So that's also a random thing. So basically, random experiment and outcome of a random experiment really is a cover for a very complex phenomenon, where we say that let's not get into this business of identifying the phenomena and how the phenomena actually will unroll. Let's just assume that the outcome can be one of several things, right? And it takes these outcomes with some probability. You have a die, a six-faced die, and you roll it. Just like with the tossing of a coin, you can also tell what the face would actually be, provided you knew enough of the launch velocity of the die, how many times it will rotate, the surface on which it is rotating, the friction on the surface, all kinds of parameters, right? And then if you knew all of this stuff, there would be some complex formula, you plug in the numbers, and then you say, it'll land up at 3. Okay. But then you say, no, it's going to be any one of 1, 2, 3, 4, 5, or 6. Okay. That's what it is. So the term random experiment is used to describe any action whose outcome is not known in advance. Okay. Counting how many times a certain word or a combination of words appears in the text of King Lear and the text of Confucius. Okay. You don't know what that number is going to be. So you say it's going to be one of several possibilities. You pull a card from the deck, right? If the deck was truly randomly shuffled, unknown to you, then you don't know what card you're pulling. But if the deck was shuffled by you, or in some order it's known, then you pull something in the middle, then you can pretty much tell what card it is, right? I'm trying to reinforce repeatedly that randomness is simply a cover for how much knowledge you have on the process, how much you're willing to use. So the last example is something, I'll leave it for yourself. Nothing really great. Can you please go off onto mute mode? One of you. Okay. Now, how do we study these random outcomes though? You do an experiment, you get an outcome. It's one of several possibilities. How do you study all these possibilities mathematically? So you define a concept called a sample space. The sample space of a random experiment is a set S that includes all possible outcomes of the experiment. So what you want to do now is to say, okay, look, you're doing an experiment, you're getting a bunch of outcomes, right? We want to be able to treat the outcomes of an experiment in a mathematical way. So in order to do that, we say, okay, look, let's define something called a sample space, which is basically a set, okay, that includes all possible outcomes of the experiment. So for example, if you were to throw a die and record the outcome, then what would your sample space be? 1, 2, 3, 4, 5, or 6, whatever number you see on the top, right? You can't see anything outside of this set. You manufacture an integrated circuit and test it to determine whether it meets its quality objectives or not. What possible outcomes are there? Either accepted or rejected, right? There's no halfway point between them. So A or R are the only two outcomes. Okay, so now you want to actually, like I said, the reason we wanted the notion of a sample space is so that we would be ultimately be able to study probabilities. Some outcome happens. A valid question is to ask for the probability of a particular outcome. What does that probability actually mean? Okay, so we have to quantify that in a mathematical way. So you need a notion of a sample space. You also need a notion of an event. Okay, since a sample space is the set of all possible outcomes, we define an event to be a subset of the sample space of a random experiment. So if I take a die, right? So I say, here is a die. All possible outcomes be 1, 2, 3, 4, 5, 6. Now I have an event. E is top face of die is an odd number. Okay, so E will be a subset of S. Okay, what will be the set of outcomes that belong to E? Well, any number that is an odd number, right? That is on the face of the die. It will be 1, 3, 5. 2, 4, 6 are even numbers, right? So you say E is an event. Now, if I toss a die and then say, does event E occur? I'll say that event E occurs when one of the elements in event E are the actual outcome of the experiment. So I tossed a die, right? And I saw that 3 appeared at the top. So I say event E occurs. Event E being that the top face of the die should be an odd number. If event 5 occurs, if the outcome is 5, I say that the event E has again occurred. If the outcome is 1, then I say the event E has occurred. Right? Now, if I ask you this question, suppose the die was, it was equally likely for the die to show any outcome, right? I roll a die and then it appears that with 1/6 of the time I see 1, 1/6 of the time I see 2, 1/6 of the time I see 3, and so on, right? Then I ask you, what is the probability of seeing the event E? What fraction of the time am I going to see an outcome that belongs to event E? Well, half of the time, right? Because I'm going to say that P of E, I can talk about a classical probability of an event as saying P of E is the number of favorable outcomes for E outcomes and the total number of outcomes. So I toss a die. What's the total number of outcomes? It's 6. What is the number of favorable outcomes? Well, it's every outcome that is an odd number, right? There are 3 such outcomes, 1, 3, and 5. Okay, so this is the size of the set 1, 3, and 5. And the denominator, the size of the set 1, 2, 3, 4, 5, and 6. So I put this absolute number kind of sign to denote cardinality, okay, the size of a set. So it's 3 by 6. So classically, right, it makes sense to say that, 1 second, I think I've lost. Can you guys still hear me? I think I've lost the connection or.
Yes, sir,
No,
we
no,
can
sir.
hear you.
Yes, we can hear you.
Okay,
Yes,
something
sir, we
happened
can
along
hear
the way.
you.
Somebody lost. Okay, fine. Let's move on. So classically, right, you can say that the probability of an event is that if I were to throw a die now, what is the probability that, what is the chance that I see that event occurring? Well, I look at all possible outcomes that are possible. I look at all possible outcomes that belong to the event. I take just the ratio of those two numbers. Now, this is in the under the provision that all the individual outcomes are equally likely. Okay, so let's work with that provision that every single face of the die is equally likely. So every single face of the die will occur 1/6 of the time. That being the case, what is the probability of my seeing an odd number on the face of the die? Right, 3 by 6. So that's the classical definition of the probability. Okay, so it's basically, here we go. So just to summarize the discussion, first of all, what is an event? It is a set of outcomes of the experiment. This includes the null set of outcomes and the set of all outcomes. So each time the experiment is run, a given event A either occurs if the outcome of the experiment is an element of A, or does not occur if the outcome of the experiment is not an element of A. Okay, so then you had this notion of experiments, outcomes, and so on. I've formalized that notion using set theory. I used a set S to denote the sample space, which is a set of all possible outcomes. Then I'm using sets E to denote specific events. Okay, so now I can use the language of mathematics to talk about probabilities and so on and so forth. So I have to formalize it, right? Now, I can also talk about the complement of an event. The complement of an event is defined to be the event consisting of all sample points that are not in A. So if I look at my example of odd face of the die, 1, 3, and 5 represent outcomes that belong to the event A.
Sir, sorry to interrupt, sir. Next class has already started. Is it possible, like, if we can take a pause here?
It starts at this class ends at 10:20, right? The next class starts at 10:20 again.
10:30. It starts at 10:30.
Okay. What I'll do is
this will
I'll
take the
take
5 minutes questions, sir, if possible.
Okay, fine. You want 5 minutes of question? We can take a pause here. Not an issue. Yeah, go ahead. If you have questions, you can ask me. Those of you who want to leave the class can do so. Those of you who want to stay and ask me questions, you can spend the next 5 minutes asking questions.
So can you please share the PPT of the first lecture on the text?
PPT of lecture 1. It seems like lecture 1 is the source of all the trouble. Okay, here we go. Yeah. Which slide do you want to go to?
No, on the Texila portal, not here.
On the Texila portal. Yeah, this is the same thing as this, right? Just annotated. Oh, you're asking me to share these slides.
Yes.
Yeah? Yes. I'll put it on the Teams side if you don't mind.
Okay, yeah, sure. You can put on Teams.
Okay, see, the thing is, I want the Taxila thing to be sort of like for all sections. Okay. And the Teams thing to be for only my section. I want to create that distinction.
Perfect, sir.
So could you go to the last curve that you drew on the OneNote?
Last curve I drew onto OneNote. Okay.
Yeah, I think it would be a page
Thank you, sir.
previously it was.
Yeah, sure. You can leave. Those of you who want to go
maybe
can go. Let me go to this last curve.
Thank
This
you,
one?
sir. This one, yes. So
Yeah.
could you please visualize how variance and standard deviation would look on this curve?
So the variance will be, see, it'll be something like this. Okay, here's what we'll do. Okay. So we histogram this curve first.
Okay.
Now in the histogram, you have a bunch of different things, right? Different numbers. Yeah. So you have x1, x2. Let's say I have n different things. I have xn. Right. So x1 represents the number of points that went into this thing. X2 represents the number of points that went into this, and so on. And then I say that, okay, so how does standard deviation actually work? So I identify the mean. Let's say this point is the mean. Okay, so mean will be, you say, okay, you have x1 point in the first histogram. Then each histogram bucket has a certain representative point in it, right? So x1 into, say, d1 plus x2 into d2 plus xn into d n, and I'm going to divide by n. This is mean.
Yes, sir.
Okay, what about variance? So I can say variance will be x1 into d1 minus mu the whole squared plus x2 into d2 minus mu the whole squared. There's a lot of noise. See, so if you're going to be in a class, please be in mute. Okay, I can't. Please, all of you, please obey this. Please be in mute. Thank you. Now, if you look at the second point, x2 d minus mu the whole squared plus xn dn minus mu the whole squared, and then you're dividing it again by n. Okay, how did I get this formula in the numerator? Well, I said, look, there are x1 points in this histogram over here. Those points are basically at each of those points is at a distance of d1 minus mu from the actual mean, right? So d1 minus mu the whole squared is the square of that deviation. So I'm saying that all of the points in the given histogram bucket are essentially placed at d1. That's not true, strictly speaking. It's an approximation, but it's an approximation that can become better and better as I increase the number of buckets. If I make the number of buckets go to infinity, each bucket is essentially zero width, right? So I can say the midpoint of the bucket is where all of the elements of the bucket actually reside. So this becomes more and more true as I increase the number of buckets. But if it's not, then I can take this as a sort of a approximate computation. I have d1 minus mu the whole squared is the deviation of one of the guys in this bucket, okay, from the mean. So d1 minus mu the whole squared times x1 is the total deviation of all of the x1 elements of bucket 1 from the mean. Then I do that for bucket 2.
Approximating everything in x1.
Yes, x1, yeah.
Okay.
Then I do that for x2, then I do that for x3 and so on. So x1 d1 minus mu the whole squared plus x2 d2 minus mu the whole squared plus all the way up to xn dn minus mu the whole squared divided by n. That will be your variance.
Yes. So it's a distribution of different histograms
from the average. Mean. Yeah, average squared deviation has been computed this way.
Okay. Got it.
Sir, I'll go next, sir. So
yeah, go ahead.
Yeah, for sample variation, it will be always the sample size will take, right? Not the population size.
Yes, sample. Anything to do with the sample has to do with the sample size only.
Yeah.
See, once you draw a sample, you don't care about the population. Now your world is only the sample. So if you take a sample mean, you'll take the sum of all the elements in the sample divided by the number of elements in the sample, because the number of elements in the population is not even known to you. Okay.
Understood, sir. Thank you.
Yeah, sure. Okay. Okay, I'm going to be late for the next class now.
Just a question. The practice questions that were at the end of the PPT, right? Do we also have the solutions for them, or are those only the practice questions added in?
Some of them have solutions, like for lecture 2, I think nearly all of them have solutions. But see, the thing is, in the lecture 1 with the box and whisker plot and so on, a lot of that is self-explanatory. So we don't have solutions for all exercises.
Okay. Thank you.
So just one request. Could you please share this PPT over the Teams?
Yeah, I'll do that. PPT and class notes will all be shared on Teams, okay, in my section. The regular slides which are coming from the IC, instructor in charge, which is common across all courses, all sections, which is not annotated, that will be in Taxila. Okay. Yeah, that will be in Taxila. Thank you.
Notation. Thanks.
Excuse me, sir.
Yeah.
So I mean, this is not much. It's not a doubt more than a request. So would it be possible for you to table all questions towards the end, sir? Because I think most of us are really happy with how the lectures are going, but the interruptions and I think
So
people
many
usually
questions
piggyback behind
are,
doubts.
yeah, so many questions are coming in the middle. It would be nice if you can take up the questions at the last.
Yeah, but yeah, I would like to ideally, but see, the thing is, if somebody has a really pertinent question that prevents them from understanding the rest of the thing, right? Maybe you want to. So what I'll do next time is that
raise
if
the
there is
hands.
so raise the hand. I'll consider the question for immediate answering. If it's really, it really has to do with broader understanding of the material. But if it's a sort of a doubt or something that we can postpone to the end of the class, I'll do that. This is a sort of a midway kind of treatment. Okay, because it's also not fair to curb the doubt of someone, genuine doubt of someone, which will prevent that person from understanding the rest of the class, right? And maybe it's also a doubt that other people have in their minds and they're not voicing it. I have to take that risk.
Sure, sir. A quick thing though. So basically, when people have doubts, they're putting it up in the chat and we are able to resolve it ourselves. So another student typically comes up with the answer also for simple doubts, but definitely for more complex ones, we would need your help.
Yeah, that's what. Yeah. Okay.
Sure, sir.
Yeah, sure. I'll do something like that. We'll speed up a little bit, because these are at the end of the day fairly basic concepts. Okay, so this is high school mathematics. Whatever treatment I'm giving in probability, you would have seen in a high school thing as well. So we'll speed up a little bit next time. I try to draw level with where we are expected in the course, but I'm not going to speed up beyond the point. Okay, so and I will try to optimize the number of questions and so on, so that we have a sort of relatively smooth experience. Okay, not an issue.
Definitely, sir. Thank you so much.
Okay, thank you all, and see you next class.